Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Let's get started right away. Today's a big day. We're going to simplify radical expressions exactly and without the use of a calculator using our knowledge of power. So we will be working with our half sheets. You want to make sure that you keep that near and dear. We'll need those perfect nth powers as we go to develop a method for simplifying nth roots today. So let's go ahead and take a look at our bar. Last class we defined fractional exponents, right? X to the 1 over n is defined to be the nth root of x, and we can simplify those expressions by using our knowledge of nth powers. So let's go ahead and take a look at the first one. 8 to the negative 1/3. 8 to the negative 1/3 is the same as 1 over 8 to the positive 1/3. And so negative exponents don't mean negative answer, they mean reciprocal. So our first step is to hop the line and change the sign. We'll rewrite that power with a positive exponent. And now we know that 8 to the 1/3 is just asking for the third root of 8. Everybody go to your half sheet. What to the third power equals 8? Go ahead and tell the class when I call on you. Ben C, 2. So I get 1 over 2, and that's my final answer. Go ahead and raise your hand if you had 1/2 for the first one. 1/2? Excellent. That's great. Negative 4 cubed. There's no negative exponent here, so there's no reciprocal. So there's no 1/4 here at all. The negative is on my base, not on my exponent, and so there's no reason to write a reciprocal here. Instead, this is just a basic exponent problem. Negative 4 to the third power means negative 4 times negative 4 times negative 4, and that is negative 64. So number 2 is just a one-stepper. We're just multiplying negative 4 by itself 3 times. Not so with number 3. Number 3, the difference is the negative is up in the exponent. And so to simplify number 3, we are going to flip the base and rewrite with positive exponent. Let's do that as our first step. So 4/25 to the negative 3/2 is the same as 25/4 to the positive 3/2. Notice how when we're simplifying an expression with negative exponents, we're not flipping the exponent. We're just flipping the base. The negative exponent means reciprocal of the base and then rewriting to the positive exponent. Now we'll go ahead and purposely choose to apply the denominator of my rational exponent as an nth root first. And so we'll go ahead and rewrite this as 25/4 to the 1/2 and then all to the numerator exponent of 3. And so we can work from the inside out by applying my denominator of my exponent as an nth root first, and then raising to the numerator exponent second. Which means that inside those parentheses, I need to find the square root of 25/4. All right, go ahead and tell the class, what's the square root of 25? Katie? 5. What's the square root of 4? Katie?
2.
Good. So we rewrite my inner power, and then lastly we need to raise it to the numerator exponent, which was the cube. So we've worked from the inside out. We've applied our denominator of my rational exponent as an nth root first, and then we're raising to the numerator exponent second, which is why my answer is 5 cubed, or we find it. What's that, Tyler? 125, thank you. Over 2 cubed, what's that? Olivia B?
8.
8, so my final answer is 125/8. What questions do you guys have about number 3? That's a rip-roaring problem right there. Okay, so it's important to note that in the absence of parentheses, the exponent only applies to the factor directly next to it. And so what's raised to the 0 power in number 4? All right, what's raised to the 0 power in number 4? Logan?
Negative 4. Just 4.
Bugger, right? Just the 4, because there's no parentheses, right? Only the thing that's right next to that exponent is raised to the exponent, and then the negative is out front as if it were a multiplier, right? The opposite of 4 to the 0. And so when we're doing this, we're really thinking like this, right? That 4 to the 0 is 1, and so this is really like negative 1. And that's different than number 5. Number 5 is 45 to the 0, and so that is 1. So we see the difference between number 4 and number 5? Awesome. If it had been negative 4 in parentheses to the 0 power, then it would have been positive 1. Okay? Awesome. Let's go ahead and do number 6 then. 1/3 to the negative 4th power. We can rewrite that, go Gadzon, as the reciprocal raised to the positive exponent. So 1/3 to the negative 4 is the same as 3 over 1 to the positive 4. And now we'll simply find that on my power sheet. Everybody find it? Tell the class when I call on you. 3 to the 4th. What's that from our power sheet? Caitlin T? 81. Awesome job. What questions do you guys have about the first half? Okay, then let's keep the party going. Negative exponents don't mean negative answer or negative value. They mean reciprocal. So 3 to the negative 2, we'll go ahead and handle that in green first. 3 to the negative 2 is the same as 1 over 3 to the positive 2 times, and 3 to the 5th is 3 to the 5th. Oh, we don't have to simplify this. These have same bases, and so it's much quicker and easier if we simply apply our exponent rules. I didn't recognize that second power had the same base, 3, and so all we need to do is multiply 2 powers together with the same base. Everybody think, what's my shortcut operation with exponents when I multiply 2 powers together with the same base? What can I do with those exponents? What do I do with those exponents? Luke? Addition, absolutely. So we'll go ahead and rewrite this as 3 to the negative 2 plus 5. And so 3 to the negative 2 plus 5 is just 3 to the 3rd, and 3 to the 3rd is on my half sheet. That's 27. So that's a much quicker and easier way. I thought that the bases were separate. I was only looking at that first one. We can simply apply our properties of exponents to evaluate that. Number 8, is the negative in my exponent? No, right? The negative is in front of the base, and there's no parentheses. Like Logan, we were talking about last half, and so we're not going to actually flip the negative. In this case, it doesn't matter. It ends up being a cube root, right? But if it were a square root, that would make a difference. This negative not included is part of the base. It's a multiplier in front. And so this is really negative, and then 1 over 20. Oh, nope. This is just negative 27 to the 1/3 power. And 27 to the 1/3 power is asking for the cube root of 27. And so this is just negative in front and then 3. And so my final answer here is just negative 3. That's not bad at all. We should have the second half, first half. Negative 6, here we go. This is what I'm after. So negative 6 to the negative 2, the negative is not included as part of my base. The negative is a multiplier in front. So I'm going to leave that negative. And now I'm going to go ahead and hop the line and change the sign on the base 6. I'm going to make that 1 over 6 to the positive 2. So 1 over 6 to the positive 2, because there's no parentheses. The negative is not included as part of the base in my original power. Only the 6 is the base in the original power. So I've got the negative out front, then times 1 over 6 to the positive 2. I can rewrite that then as negative 1 over 36. And my final answer is negative 136. There, these negatives can be tricky. What questions do you guys have about number 9? Okay, number 10, we'll apply my properties of exponents to raise a power to a power. Go ahead and tell the class my shortcut operation between the exponents when there's parentheses there. What's my shortcut operation between the exponents? Margot?
Multiplication.
Multiplication, thank you. So we'll rewrite this, and my first step is 3 to the negative 1 times 4 is negative 4. So 3 to the negative 4. I know that that means not negative answer, but reciprocal. So 3 to the negative 4 is the same as 1 over 3 to the positive 4. And look at it told us before, then that is 81. So 1 over 81 is my final answer. Continuing on with our properties of exponents, number 11, 10 to the 3rd over 10 to the negative 2. I know that with the quotient of powers, my shortcut operation is subtraction with the exponents. Top exponent minus bottom exponent. And so I could first rewrite number 11 as 10 to the 3 minus a negative 2. Top exponent minus bottom exponent. But when I do that, notice how subtracting a negative is the same as adding a positive. And so I would get 10 to the 5th power. And so I go to my half sheet, 10 to the 5th power. What did you get for that, Taylor?
100,000.
Awesome. That would be 1 followed by 5 zeros, right? 10 to the 5th power would be 1 followed by 5 zeros. Nice job. Thank you. All right. Now, the moment you've all been waiting for. No, not that moment, Braden. The moment you've all been waiting for is simplifying that radical 18 exactly without the use of a calculator by breaking it up into perfect nth powers. If we're going to simplify a square root, we know that we can't have any perfect squares as factors hiding inside the radical. Are there any perfect square numbers that are factors of 18? Well, let's go and let's think of our perfect square factors. 1 squared is 1, right? 2 squared is 4. Does 4 divide evenly into 18? Is that a remainder? No. 3 squared is 9. Does 9 divide evenly into 18? Yes, and so 9 is going to be a perfect square factor that divides evenly. So I've got 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 36, and so on. And so my perfect square factors, right, if they're hiding inside of a square root, then I know that square root can be simplified algebraically without the use of a calculator. So let's rewrite that root 18 as a product. Let's rewrite that root 18 as root 9 times 2. By rewriting that 18 as 9 times 2, I can see the perfect square factor, 9, hiding inside of a square root. And I know that a square factor inside of a square root will simplify to an integer out front. And so in accordance with the product property, I could then go and rewrite this as root 9 times root 2. And that's kind of an extra step, but we can see explicitly where this is coming from. One of these radicals simplifies, and I'll give you a hint, it's not the second one, right? The square root of 9 is an integer, and that equals 3 times root 2. So my final answer is 3 root 2. That, in essence, is what we're going to be doing today when we simplify radicals exactly and algebraically without the use of a calculator. It's just that we won't have square roots all the time. We'll have cube roots, or fourth roots, or fifth roots, etc. And so we need our power sheet in order to get our perfect nth powers. We won't be looking at our list of perfect square factors. When we simplify a fourth root, we're going to be looking at a new list, a list of perfect fourth powers, right? And that's what will break up our number inside into a product of perfect nth powers in order to simplify an nth root, and that's where we're headed. What questions do you guys have in your Bellwork today? That was a rip-roaring Bellwork. Let's go ahead and take care of some business. And so what I'd like for you to do at this time is take out your assignment number 5. Please make sure that your name first and last, 1A and number 5 are clearly labeled at top. Give yourself credit for those who complete out of 48 in pencil, please. Divide, enter, multiply by 4. And then if you did your reading questions, 8, 4, and 8, 5, you can go ahead and add an additional point. If you just did one reading question, then you'd be adding a plus half, 0.5. And if you didn't do your reading questions, then your max infinite canvas score will be out of 4. Please make sure that you round to the nearest half point and then box your answer nice and big on top. If you have multiple pages, please take this opportunity to staple them together. There's a stapler on the front table and a stapler on the side activity table. And please do that during our homework check so we don't have to wait at the end when it's time to collect. So you can go ahead and do that now. And what questions do you guys have about your campus score? And let's go ahead and put our pencils down then. Pencils down, and now it's time for our grading pencils. And soon we'll be advancing the slides, so make sure you're checking. And next slide. And soon we'll be advancing. We'll go guys around.
I know. Like. And the last part of 7/8. You guys ready?
Yep.
Not quite the last part. Who assigns these? Omega assignments. Okay, and finally. As you're finishing up, go ahead and give yourself an accuracy fraction on how many you did. About how many did you get correct, and pen circle it. Make sure your infinite campus score is boxed and pencil nice and big at the top. Multiple pages should be stapled together. Final check with your name, first and last, 1A, number 5 clearly labeled. Then please pass from the back to the front. Front rows, if you make sure they're facing the same direction, I really appreciate your help. Thank you. Number 5. I got number 5. Awesome. Thank you for your help, ladies and gentlemen. Thank you for your help. I appreciate that. Okay, ladies and gentlemen, now let's focus in on our content objectives for the day. And so by the end of today's class period, you're going to be comfortable evaluating radical expressions without the use of a calculator, exactly and algebraically, through your knowledge of nth powers. And so you need your half sheets, because we're going to have to simplify our radicals without the use of a calculator. So we saw last time, right, that x to the 1 over n power was defined to be the nth root of x. Today we're going to actually write that as a radical. So a radical can be written as an nth root as well. When x is non-negative and n is an integer greater than or equal to 2, so now we're dealing with square roots or higher, then the nth root of x is defined to be x to the 1 over n power. So we're going to restrict our fractional exponents to include positive bases, but we could rewrite x to the 1 over n as the nth root of x. So in this chapter, we're going to focus on the radical format and how we can simplify expressions with radicals. So the next concept has been a concern to many. Let's go ahead and try to sort this issue out. Which nth root does the nth root of x represent? And so typically, if we're given an expression that involves x to the 1nth power, or the nth root of x, we're talking about the positive principal root. And so while, when solving the equation, x squared equals 4, we have two separate answers. Those are given by the x values of those intersection points, x equals 2 and negative 2. You're the one creating the square root. You're the one doing the positive and negative square root to undo a squaring power, right, when we solve the equations, and so we had to be on the lookout for two solutions. Versus if you're given an expression, with the radical in it, like the square root of 4, then there's just a single value of this. A single value is the positive principal square root of 4, and that's defined to be 2. So you can kind of see this visually. There's one, right? There's one value when you're evaluating the square root of 4 versus when you're undoing a power expression, x squared equals 4, by considering roots, positive and negative square roots, then you need to add the two different solutions. And so in this case, if x equals root 4, then x is given by a single value, that's 2, versus if x squared equals 4, then that's given by two separate answers, x equals plus and minus 2. So do you see the difference? When you're the one making the roots to undo a squaring or a power, that's when you might need to consider two solutions, versus if you're simply evaluating a single root, then there's just one value. And so that's kind of a good guide as you're working to evaluate these nth root of x. All right, so the root of a power theorem we saw last time. We could simplify x to the m over n by first taking the nth root of x and then raising to the m, or by taking my base x, raising it to the m, and going back and finding the nth root last. In either case, right, we can now rewrite without fractional exponents, but rather with a radical expression. And you'll have to do so in your closure today. And so x to the m over n from yesterday can be rewritten as the nth root of x to the m, or the nth root of x all raised to the nth power. Again, when evaluating without a calculator, which expression is the easiest to simplify? And so if you look at these two things, the first or the second, which one would be easier to do without a calculator? Go ahead and tell your partner quietly. Right? The first or the second one, which one would be easier to do without a calculator? They both equal x to the m over n from last class. Which one would be easier to evaluate without a calculator? Margot and Katie?
The second one.
The second one? How come?
Because if x is like a larger number, you get to make it smaller and then bigger, instead of having to do it bigger and then smaller.
Absolutely. And so just like last class, when we did x to the 1 over nth power first, and then raised to the numerator exponent, the m last, so too will we take the nth root of x first, and then raise to the mth power last. That's exactly right. So the easiest way is going to be that second way. That second way is going to be our strategy. So this is the one we'll be doing non-calculated. Nice job. Thank you. All right. Let's go ahead and remind us of some properties of exponents now. So we're going to see if the square root of 9 times 16 is equal to the square root of 9 times the square root of 16. And we're going to decide that with a true or false. So go ahead with your partner right now. I want you to determine if those two sides of the equation are in fact equal. If they are, then I want you to denote that as a true by the box. And if it's not, I want you to put that as a false by the box for each of these four things. And you can use your calculator to check, or you can do it through inspection if the numbers are smaller. So decide if each one of these equations are true. If they are, right, put a true. If they're not equal, then put a false. Be ready to share with the class. Okay, the moment of truth. Ooh, true or false? Go ahead and share the first one. Does the square root of 144 equal question mark 3 times 4? What did you and your partner decide? Mark and Taylor?
True.
True. What are you going to get? True for the first one. T for true. Awesome. Second one. Did the square root of 25 equal question mark 3 plus 4? Carson and Dakota?
False.
False. That's false. Raise your hand if you have false for the second one. False. Good job. So we cannot distribute that radical through that addition, right? Through that addition. That does not hold true the way that it does for multiplication. Third, does the square root of 16 equal question mark 5 minus 3? Cody and Aaron?
False.
False. So raise your hand if you have false for the third one. Definitely false, so we can't distribute a radical through subtraction either. And lastly, what about a quotient? Does a radical apply to a quotient the same way that we get a quotient of radicals? Let's see. Does the square root of 4 equal question mark 10 divided by 5? Logan and Barrett?
Yes.
Yes, so true for the last one. Raise your hand if you have true for the last one. Awesome, Blossom. Let's get cracking. So we have two different rules called the product property of radicals and the quotient property of radicals. That is, a radical can be distributed through addition or subtraction, or we can break up a product inside of a radical as a product of two radicals, or a quotient inside a radical as a quotient of two radicals. We cannot break up a sum or difference inside a radical as a sum or difference of two radicals. So we can't break up addition or subtraction in a radical. All right, let's go ahead and see if we can apply these properties. So the square root of 75 can be simplified exactly and algebraically by taking a look at our perfect square powers. Everybody look at your perfect square powers, and we want to find the largest one that divides evenly into 75 without a remainder. So I look at my perfect square powers, and I want to find the largest one that divides evenly into 75. So I usually start on my list, and I look at my squares on my half sheet, and I start at the lowest one, the biggest perfect square beneath 75, and that's 64. That doesn't divide into it evenly. Then 49, that doesn't divide it into it evenly. Then 36, that doesn't divide it into it evenly. What's the greatest perfect square that divides evenly into 75 without a remainder? Olivia H? 25, awesome. And we see that in our list of perfect square powers. So let's go ahead and rewrite my root 75 as root 25 times 3. So we've rewritten 75 as 25 times 3. How come? Because now the product property allows me to break that up as a product of radicals. That's root 25 times root 3. And one of these simplifies to an integer, right? And so we've enabled ourselves to rewrite this as 5 root 3. And that's what you guys did in geometry with simplifying radicals. Let's take a look at root 2 times root 18. The product property works in reverse. And so, not only can I take a product inside of a radical and break it up into a product of radicals in blue, as we did with number 1, I can take a product of radicals and rewrite it as a single radical. That is root 2 times root 18 equals root 2 times 18. And so inside, I can do 2 times 18 and get 36. Why is that useful? Well, now, because 36 is itself a perfect square. Square root of 36 is an integer. What is the square root of 36? Well, look at your perfect square powers on your half sheet. And what is the square root of 36? Olivia B? 6. And so my final answer would be 6 for number 2. And we did it without a calculator. That's pretty sweet. I can apply the quotient property. The quotient property in reverse as well. A quotient of two radicals can be rewritten as the quotient of a single fraction. I'm sorry, a radical of a single quotient. Here we go. Root 99 over root 11 is root 99 elevenths. And why is that useful? Because the square root of 99 elevenths is the same as the square root of, let's reduce that fraction. 99 divided by 11 is 9. And the square root of 9 is an integer. So the square root of 9 is 3. And that's useful. That's way simpler than root 99 over root 11, isn't it? 3. The square root of 50 times the square root of 1/2, we could rewrite that as a product inside. So that's a single radical. 50 times a half. 50 times a half is 25, and that itself is an integer. So that would equal 5. And lastly, an equally important property, a square root times itself. In essence, a square root squared, right, gets rid of the radical and gives you the quantity inside. And so we can do it the long way to verify, but ever after we won't do it any longer. Square root of 7 times the square root of 7 is the square root of 7 times 7 is 49. And what's the square root of 49? And that's 7. And so there's nothing special about 7. A radical times itself, right, is a radical squared, and that will undo the square root and get that quantity inside. So if that were root 13 times root 13, we could just write 13. If we're root 253 times root 253, we don't know what 253 squared is on your sheet, but we don't have to figure it out because when we square a square root, we get the number inside. So it's just, we can jump right to the answer. What questions do you have on these first 5? So that's old news. That's old news from geometry. What we're going to do today is extend it to nth powers. And so we're not just going to be dealing with our nice familiar comfort zone perfect squares up here in blue. We're going to extend this to include perfect cubes or perfect fourth powers. And we're going to simplify, right, nth roots, fifth roots, sixth roots, and so on and so forth. So our product rule for radicals and our quotient rule for radicals applies for any nth root. We could rewrite the nth root of a times b as the nth root of a times the nth root of b, or the nth root of a quotient a over b as the nth root of a over the nth root of b. So the root of a product theorem can be rewritten then as fractional exponents or with radicals. And we're going to go ahead and use our half sheet to help us simplify perfect nth roots. In order to simplify an nth root algebraically, we must find factors that are perfect nth powers. Just like we simplified the square root of 75, because it was a square root, we were looking for perfect square factors that divided evenly into 75 without a remainder. So too, we'll be looking for perfect cube factors inside of a cube root in order to simplify algebraically. And so it's true that the cube root of 2 times the cube root of 120 equals the cube root of 240. That first line, everybody look, that first line is true. It's also true that the cube root of 8 times the cube root of 30 equals the cube root of 240. And finally, the third line is also true. The cube root of 16 times the cube root of 15 also equals the cube root of 240. However, only one of these 3 rows, first, second, or third, would be any use to us when we're trying to simplify algebraically. The key here is that we're trying to simplify a cube root, and so in order to do that, we need a perfect cube that's a factor of the number inside of that radical. And so which of these factors here is a perfect cube inside of a cube root? Everybody find it. Right? Only one of these factorizations is going to be useful when we go to simplify the cube root of 240. Only one of them contains a perfect cube inside of a cube root. Ben C?
The second one.
The second one is the only one that's useful to us algebraically to simplify this. All of them are true because of the product of radicals property, but only the second one contains a perfect cube inside of a cube root. That's the only one that's going to be useful for us as we go to simplify. All right, so the index on my radical. The index is just a special name for the kind of radical it is, right? The type of root. This is a cube root, so we're looking for perfect cubes. So let's go ahead and consider my perfect cube list. We had our perfect square list on the front whiteboard in blue. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, ... forever. Let's make a perfect cube list. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. 4 cubed is 64. 5 cubed is 125, and so on and so forth. And now you have the rest on your sheet. Go pretty high. If I want to simplify a perfect cube, I'm looking for the largest perfect cube that's a factor of the number inside of the cube root without a remainder, that divides evenly into it without a remainder. Let's go ahead and finish this one out then. So in this first factor, this middle factorization, Ben told us this is the only one that's useful. Why? Because the cube root of 8 is equivalent to 2, and the cube root of 30 doesn't contain any more cube root factors. Perfect cube factors. So my final answer, fully simplified, would be 2 cube root of 30. That's as far as we can go. Let's go ahead and try simplifying some square roots. So here we go. Square root of 48. This is going to drive the discussion. So am I looking at my blue list or my green list if I'm trying to simplify the square root of 48?
Blue.
The blue list, because it's a square root, I'm looking for perfect square factors. So I'm going to go ahead and scan my perfect square list, and the largest perfect square that divides evenly into 48 without a remainder isn't 4, it's 16. 16 divides evenly into 48 without a remainder. In fact, 48 is 16 times 3. So I'm going to rewrite square root of 48 is square root of 16 times 3. Why is that useful? Because the square root of 16 inside of a square root is equivalent to an integer out front. What is the square root of 16? Well, that's 4, and I still have the square root of 3 inside. So we rewrite our 48 as a product, where 1 is the largest perfect square that divides evenly into 48 without a remainder. And then that perfect square inside of the square root, squiggle underline blue, comes out in the integer out front, and the 3 stays inside. Let's do the same thing, but let's do it with the cube root of 48. Now am I going to be looking at my blue list or my red list to simplify a cube root? Now it's time for my red list. I'm looking for perfect cubes that divide evenly into 48. So everybody, we're going to start. I'll start the next highest perfect cube beneath 48. Does 27 divide evenly into it? No. Does 8 divide evenly into it? Yes, and so I'm going to rewrite the cube root of 48 as the cube root of, and I'm going to break up that 48 as 8 times 6. By rewriting 48 as 8 times 6, I've broken it up into a product of factors where 1 is a perfect cube. How come? Well, because a perfect cube inside of a cube root will simplify to an integer out front. This would have done me no good to break it up as 16 times 3, because 16 is not a perfect cube, and 3 is not a perfect cube. But by breaking up the 48 to 8 times 6, now I have a perfect cube factor inside of a cube root. That comes out to an integer. What's the cube root of 8? That's 2, and then I still have the cube root of 6 inside. Awesome. And one number to go, and then we'll do some variable expressions. The fourth root of 48 isn't going to be handled by my blue list or my red list. I'll have to go to my black list. So the perfect fourth powers are 1 to the fourth is 1, 2 to the fourth is 16, 3 to the fourth is 81, 4 to the fourth is 256, is it? 256? And that's probably good for right now. All right, so I'll go ahead and scan my fourth power list, and the numbers get big very quickly, so I only have a couple options. Looks like I only have one option. Does 16 divide evenly into 48? It does. That I'm choosing 16 not because it's a perfect square, but because it's a perfect fourth power, and I'm trying to simplify a fourth root. Everybody, let's rewrite that 48 as the fourth root of 16 times 3. A 16 inside of a fourth root, right, is equivalent to an integer. What's the fourth root of 16? 1, 2, 3. Looks like 2, right? 2 is the fourth root of 16, and so that 16 inside of fourth root comes out front as a 2, and I still have the fourth root of, and inside is still 3. So the third one is a very different answer than the first one, right? In the first one, we were simplifying a square root, so we look for perfect square factors. In the third one, we were simplifying a fourth root, so we look for perfect fourth powers. Awesome. Let's go ahead and do the same with variable expressions. Variable expressions are a little different because with my variable expressions, right, we're looking for the largest perfect cube that's a factor of that power x to the 11th. In order to do that, I know that a perfect cube is going to be an exponent that's divisible by 3, all right? And so I'm looking for the next highest exponent beneath 11 that is divisible by 3. I know that's a perfect cube. And so is 11 divisible by 3 without a remainder? Nope. So I'm going to go ahead and chunk this down into a product of powers, of x powers, where I rewrite x to the 11th as a product of powers, where one exponent is the next highest exponent beneath 11 that is divisible by 3. So is 10 divisible by 3 without a remainder? No. Is 9 divisible by 3? Yes. 9 is divisible by 3. 9 is divisible by 3 without a remainder, so I'll rewrite x to the 11th as x to the 9th times x to the 2nd. Isn't that x to the 11th? By doing this, I can rely on this x to the 9th power as a perfect cube, right? I can think of this cube root as a 1/3 power, and I know the 1/3 power, x to the 9th to the 1/3 would be x to the 9/3. 9 is divisible by 3, and I get x cubed. That is to say, I can divide my exponent now, x to the 9th, by the index on my radical, this squiggle underline x to the 9th. The cube root of that is x to the 9/3, which is x to the what? Third. X to the 3rd is the cube root of 9. I still have times the cube root of that x squared inside. X squared is not going to simplify. Its index is less than, right? Exponent is less than the index. This is not going to simplify any further. So my strategy was to rewrite my power as a product of powers where the next highest exponent beneath the index that is divisible by the index is one of the factors, and then that'll come out as a whole power output. That's tricky. Let's do another. So we're going to do the cube root of, this is a super important one. We're going to do the cube root of 48x to the 11th. Okay? We've got two things going on here. We've got 48, which is a regular number. I'm looking for perfect cubes that divide evenly into 48. And I've got x to the 11th. X to the 11th then is a power, so among my exponents, I'm looking for the highest exponent beneath 11 that is divisible by 9. So we've done each of these kind of together. Now let's go ahead and put it all together in a single problem. Here we go. This will be the cube root of, and let's break up that 48. The 48 we're going to rewrite as what times what? Well, which list are we going to do? The blue, the red, or the black? If we're simplifying the cube root of 48. Which list are we going to be using? The red list, that middle list of perfect cubes. The highest perfect cube that divides evenly into 48 without a remainder is 8. So we're rewriting 48 as 8 times 6. We're going to rewrite this x to the 11th as x to the next highest exponent beneath 11 that is divisible by 3. We just did that, x to the 9th times x to the 2nd. And now we'll go ahead and squiggle underline those perfect cubes that are inside my radical. 8 is a perfect cube. X to the 9th is a perfect cube. These squiggle underline factors are going to come out front as whole powers. And the remainder, 6 and x squared, are going to be stuck inside my cube root in my final answer. They won't simplify. So my final answer is 2x cubed times the cube root of, I still have inside, a 6 and an x squared. That won't simplify any further. Okay, we're going to have to practice this, particularly with those variables. So let's go ahead and take a look at some of these to simplify. We're all going to do the yellows, right? And the greens are stretchers. And so we're going to do the yellows. Let's go ahead and simplify the cube root of 343. So the cube root of 343, we're going to find the greatest perfect cube that divides evenly into 343, although it appears that 343 is itself a perfect cube, isn't it? So this one simplifies to an integer straight up. We don't have to go any further. So what's that, Katie? 7. Good. So the cube root of 343 is 7 without the use of the calculator. The cube root of 512, everybody find it. That's an integer as well without the use of a calculator. So what's the cube root of 512, Mark? 8. Thank you, it's correct. The 6th root of 64, everybody find it. The 6th root of 64. Jackson. 2 is correct. Thank you. 8, the square root of 169. Everybody find it. The square root of 169. Logan.
13.
True that. Good job. Quotient property, the 6th root of 64 over 729 is the 6th root of 64 over the 6th root of 729. Let's go ahead and find it. What's the 6th root of 64? The 6th root of 64, Adam? 2, thank you. Over, what's the 6th root of 729? Everybody find it? Aaron? 3, good job. And so 2/3 would be the 6th root of 64 29ths. Go ahead and write number 6 and number 9 on your own. Be ready to share with the class. 6 and 9. 6 and 9, be ready to share with the class when I'm calling you. All right, number 6. What's the 5th root of 243 30 seconds? 243 30 seconds. What's the 5th root of that? Luke? Raise your hand if you had 3 over 2. 3/2 is correct. Good job, you guys. What's the 4th root of 10,000? What's the 4th root of 10,000? Brady? 10. Nice job. Raise your hand if you had 10. Awesome. So you guys are good with perfect nth powers. Now let's go ahead and simplify some expressions where I don't have a perfect nth power right away. We need to break up that 250 into a product of factors, where one of which is the perfect cube. I want the largest perfect cube that divides evenly into the number inside of my cube root without a remainder. And so is 250 itself a perfect cube? No, but I'll go and look at my list and see that the next highest perfect cube, right, that divides evenly into 250 is 125. So I'm going to rewrite my cube root of 250 as the cube root of 125 times 2. The reason we do that, because 250 is a lot of things, right? It's 25 times 10, but that's no use to me. 25 is a perfect square, not a perfect cube, so it won't help me simplify this at all. But by rewriting it as 125 times 2, I have a perfect cube inside of a cube root. That squiggle underlined blue is going to come out as an integer. What's the cube root of 125? Carson, you?
5.
5, thank you. And I still have cube root of 2, and that won't simplify. And so my final answer is 5 cube root 2. Good job. Variable expressions are different. I'm looking for exponents that are factors of my index on my radical. Right now, x to the 12th is already a perfect 6th power. How do I know? Because the index on my radical, 6, will divide evenly into my current exponent, 12, without a remainder. That is to say, x to the 12th, the 6th root of that is x to the 12 sixths. And what's x to the 12 sixths? X squared. And so this simplifies to x squared for the blue power. The red power, y to the 6th, inside of a 6th root, will also simplify to a whole power out front, because the current exponent, 6, is divisible by the index. That's like y to the 6 sixths, which is just y to the 1st, which is why number 9 simplifies to x squared y in one step. So I'm considering exponents that are divisible by the index on a radical when simplifying variable power expressions. All right, let's go ahead and do the 4th root of 5 times the 4th root of 125. Is 5 a 4th root, a 4th power? No. Is 125 a perfect 4th power? No, it's a perfect cube, but not a perfect 4th power. And so I can't simplify either of these radicals on their own. However, I can apply the product property in reverse. That is, 4th root of 5 times 4th root of 125 equals the 4th root of 5 times 125. And so by rewriting this as a single 4th root, I generate a perfect 4th power. 5 times 125 is 1, 2, 3, 4, 5, and 625. It's 625, and voila! Look on your half sheet. Lo and behold, 625 is itself a perfect 4th power. What is the fourth root of 625? Eric?
5.
5. Nice job. That was pretty sweet. All right, 13. Again, 2 is not a perfect cube. 4 is not a perfect cube. Let's go ahead and rewrite this using the product property as a single radical, and then we'll reduce secondly. I know some of my powers are going to reduce too, but let's write it as a perfect cube first. So here we go. I'm sorry, as a single cube root first. Here we go. So inside, I'll have 2 times 4 is 8. Inside, I'll have u to the 7th times u squared is u to the 7 plus 2 is u to the 9th. Now we'll go ahead and consider my numbers inside and see if any are perfect cubes or contain perfect cube factors. Is 8 a perfect cube? Yes, so I'll go ahead and squiggle underline that. I know that's going to reduce to an integer out front. Is u to the 9th a perfect cube? That is its exponent divisible by the index?
Yeah.
Yes, it is. It's already a perfect cube. We win. So this is going to simplify in one step. The cube root of 8 in green is 2. The cube root of u to the 9th is u to the 9/3 is u cubed. And that's a fully simplified form. No radical part remains because there are no leftovers. Awesome. Let's do 15. Is 54 a perfect cube? Look at your sheet. No, 54 is not a perfect cube. However, does 54 contain perfect cube factors other than 1? Well, yes, it does. We'll look at my red list. 64 is too high. 27. Does 27 divide evenly in 54? Good. So we'll rewrite that 54. We'll rewrite that 54 as a product with perfect cube as a factor. So that would be 27 times 2. There's my 54. Now we'll rewrite that x to the 8 as a product of powers. A product with powers with like bases where one of my exponents is divisible by the index on my radical. Is 8 currently divisible by the index 3 without a remainder? No. So I'm going to chunk down that x to the 8 as a product of powers. What's the next highest exponent beneath 8 that is divisible by 3? 6. So I'll rewrite that x to the 8th as x to the 6th times x to the 2nd. Do you agree that x to the 6th times x to the 2nd is x to the 8th? Yes, but by rewriting this as x to the 6th, I can now simplify the squiggle underline x to the 6th inside of a cube root. This is x to the 6/3, which is x squared out front. All right, let's go ahead and finish it up then. So I've got my squiggle underline red. The cube root of 27 is 3. The cube root of x to the 6th is x to the 6/3, which is x squared. Still have the cube root of, and what's still inside? Still have a 2 and still have an x squared. Woo! That was pretty sweet. That's a great problem. So we had to deal with numbers and variable expressions inside of a single radical. Getting hot in here. Love it. Need my Nelly Band-Aid. Ah, another day. All right. So is 4 itself a perfect cube? No. Is 2 a perfect cube? No. Let's apply my product property in reverse. Let's rewrite number 19 as a single radical. Ready? Go. The cube root of 4x squared times the cube root of 2x is a single cube root. 4 times 2 is 8. X squared times x is x to the 3rd. And now I have some perfect cubes inside. What is the cube root of 8? 2. What is the cube root of x cubed? Well, that's x to the 3/3. Right? The cube root of x cubed is x to the 3/3, which is just x. So big. Math works. So I'm feeling really good about this discussion. Any questions you have so far? All right, then we've got a half to go, you guys. So we've got a fourth root, we've got a fourth root, we've got a fifth root, goodness gracious, a ninth root, oh gosh, I know we can do it. So let's go ahead and simplify number 6 and number 10 on your own, and then stop. We'll come together and do 14 together. So I want you guys to do 6 and 10 with your partner. We'll check those, and then we're going to go ahead and do 14 together. Show me you get it. You need your half sheet. Okay, ladies and gentlemen, let's go ahead and do a check with 6 and 10. We held off on 14. We're going to do that one together. Everybody take a look at number 6. I'm scanning my list of perfect fourth powers to try and find the largest perfect fourth power that divides evenly into 48 without a remainder. So I'm looking at my black list, and it looks like 16 divides evenly into 48 without a remainder. So I break up my 48 as 16 times 3, and then voila! A 16 inside of a fourth root is equivalent to an integer 2 out front. I still have the fourth root of 3 remaining. So raise your hand if you had 2 fourth root of 3. 2 fourth root of 3. That's my final answer. Good job, and without a calculator. My 81 is already a perfect fourth power. So I'm going to rewrite the fourth root of 81 as 3 out front. However, my m to the 5th, right, my current exponent 5 is not divisible by my index on the radical, that 4 without a remainder. So I'm going to chunk it down into a product of powers. The next highest exponent beneath 5 that is divisible by 4 is 4 itself. So I rewrite m to the 5th in green. Everybody look. M to the 5th is m to the 4th times m to the 1st. The reason we do that is because my double underline m to the 4th is now a perfect fourth power. What's m, the fourth root of m to the 4th? Well, that's m. And so out front I get 3m, and then inside I still have the fourth root of m to the 1st. I'll write that as the fourth root of n. So that one was kind of tricky with the 5th power. I'll rewrite the 5th power. M to the 5th is m to the 4th times m to the 1st. That'll come out as one whole m out front, and I'll still have an m inside my fourth root that will not reduce. That's the end of the road. Raise your hand if you had the 3 part. If you had the 3 part, good. Who had the m out front and the m inside? Good. Don't forget the index on the radical. Lots of people lost points last year on the test because when they simplified this fourth root, they dropped the 4 on my radical and just wrote it like a square root. That's wrong. This is not a square root, it's a fourth root. So you have to keep that index throughout the problem. Awesome. All right, let's take a look at 14. Here we go. I'm going to rewrite this as a single 5th root. So my first step would be to rewrite this as 5th root of, inside I've got 3 cubed times 3 to the 4th. That is 3 to the 3 plus 4 is 3 to the 7th. I've got x to the 1st times x to the 8th. That's going to be x to the 1 plus 8 is 9. Okay, guys. Inside, do I have any perfect 5th powers? Well, I'm not going to go and rewrite 3 to the 7th out. Instead, I'm going to use the fact that 3 to the 7th is a power whose exponent, 7, is greater than my index. I know this is going to simplify to a perfect 5th power. Just like I broke up my m to the 5th as m to the 4th times m to the 1st, I'm going to break up my 3 to the 7th as 3 to the 5th times 3 to the 2nd, because that 3 to the 5th is a perfect 5th power. What? Let's rewrite that as the 5th root of, and I'm going to break up that 3 to the 7th as 3 to the 5th times 3 to the 2nd. I'm going to break up that x to the 9th as x to the, what's the next highest exponent beneath 9 that is divisible by 5? We have got to go all the way to 5 times x to the 4th. So we'll go one at a time. 3 to the 5th is a perfect 5th power. X to the 5th is a perfect 5th power. So my final answer would be, out front comes a 3. Out front comes an x. Inside, I still have a 5th root of 3 squared is 9, and x to the 4th. Wow, that was a rip-roaring problem if I've ever seen one. Awesome. Number 18. Number 18, 2 to the 12th. Is that a perfect 9th power? No, because my current exponent 12 is not divisible by 9 without a remainder, but the next highest exponent beneath 12 that is divisible by 9, right, is, what, 9? So I could rewrite this as the 9th root of 2 to the 9th times 2 to the 3rd is the exponent on the x power currently divisible by 9 without a remainder? No. So I'll rewrite that x to the 14th as x to the 9th times x to the 5th. And lastly, we'll rewrite this y to the 10th. 10 is not divisible by 9, but I can rewrite it as y to the 9th times y to the 1st. All right, guys, let's go ahead and simplify that. 2 to the 9th inside of the 9th root is equivalent to 2 out front. X to the 9th inside of a 9th root is equivalent to x out front. Y to the 9th inside of a 9th root is equivalent to y out front. And I still have 9th root of. Inside, I've got 2 cubed is 8. X to the 5th, y to the 1st. And we can stick a fork in it because we're finally done. Wow. Shake it out. Take a breath. Woo! Good job, you guys. That was serious. Let's go ahead and attack our closure then. So we're going to rewrite radical notation 2 different ways. And this was earlier in our discussion. X to the m over n can be rewritten with radicals, right? With radical symbols. Go ahead and write 2 different expressions that involve radicals that are equivalent to x to the m over n. Don't say it out loud. Go ahead and write 2 different ways. Then we're going to go ahead and circle which one of these is true. And lastly, what does it mean to be in simplest radical form? So let's go ahead and see a written response for each of these. We just have one thing we're concerned about with simplest radical form at this stage, and be ready to share with the class. Okay, let's go ahead and share responses then with our classmates. So write the radical notation for x to the m over n, right? How can we rewrite that x to the m over n using radicals? What would that look like? Heather? Good, we can rewrite it as the nth root of x all to the n. Or, that's equivalent to, right, what other way could we rewrite that as? Barrett?
N to the square root of x.
Yes, the nth root of x to the n inside. So both of these are equivalent, right? But they're strategically different in their evaluation. This would be finding the nth root of x first, taking that value and raising it to the nth power. This would be raising x to the nth power first and then going back and finding the nth root. Both of them are equivalent. Which way is easier to do non-calculator? Right? Which way is easier to do non-calculator? Bless you. Braden?
The left one, if you get a smaller number, then you do the exponent of that.
Absolutely. The left one makes smaller numbers first instead of making bigger numbers first. Absolutely. All right. Which of the following is true? First or second? Jackson? Good. The first one, the product property holds true for radicals. There is no sum property for radicals. Don't do that. Don't do this. This does not equal that. Good heavens. No way, Jose. And lastly, what does it mean to write a radical in simplest radical form? A radical is fully simplified if it doesn't contain any perfect nth powers. And so no perfect nth powers inside of an nth root. So no perfect nth powers inside of an nth root. So a fourth root is fully simplified if it doesn't contain any perfect fourth powers as factors inside. A fifth root is fully simplified if it doesn't contain any perfect fifth powers inside. Awesome. You guys have got a nice chunk of time for working on your assignment number 6. I'm going to go ahead and stop the recording here and save the notes. Nice job today. Let's go ahead.